Okay, so in the previous video, we looked at the disk method, which is a method of finding the volume of a shape that has been revolved around an axis. And if you remember, we did that by adding together the volume of disks, which are actually cylinders, and we had infinitely many. So if you remember, the volume of a cylinder is pi r squared h. Well, in this case, the h is our change in x, or our dx, okay? So when we look at our formula, we're actually looking at pi r squared dx, right? And we are summing together infinitely many of those on an interval from a to b. So our volume looks like this, okay? So today we're going to look at volume where we have to use what we call the washer method. And the washer method is used when we have an area that's bound between two curves like this, and then it's revolved around an axis. And when that happens, it leaves essentially a hole. So we have what looks like a washer. And then what we're going to do is we're essentially taking the area of the larger cylinder, and then we're going to subtract out, or the volume of the larger cylinder, and then we're going to subtract the volume of the smaller cylinder, leaving us with this space right here. Okay, so let's look at some examples. I think that's the best way to do it, okay? And again, we have to pay attention to the axis of revolution, okay? So let's look at the first example. We've got the volume of a solid generated when region between the volume of a solid generated when region between the graphs of f of x equals 1/2 plus x squared and g of x equals x over 0, 2 is revolved about the x-axis. Okay, so f of x equals 1/2 plus x squared. So let's just kind of get a general idea of what that's going to look like right here. So here's 1, here's 2. So that's going to be a parabola that's kind of starting at 1/2, and it doesn't have to be perfect, but it's parabolic, okay? So this is our f of x, and then g of x. G of x is going to be the line y equals x. Let's see, 1, 2, I wanted a different color here. Okay, so I think my graph is probably a little bit too inaccurate. Let me get a more accurate graph, okay? So let's do g of x. We get 0, 0, 1, 1, 2, 2. So here's my g of x graph. Okay, and then the f of x graph, so I've got 0, 1/2. Okay, 1 will be 1.5, and then 2 will be 4.5. So we're looking at a curve that a little bit more severe than what I had. Something like this, okay? Okay. And we're looking for the region bound between 0 and 2. Well, here's 2 right here. Okay, it's not a very good drawing. I'm not very good at drawing these, I'm sorry. Okay, say it's more or less like that, okay? So the region that's bound there is this space here. Okay. Okay. Now we're going to go ahead and we're going to revolve that around the x-axis. Okay, so if we rotate that around the x-axis, right, I've got my g of x. Okay, that's this one right here. It's not going to be perfect, but we'll get the idea. Okay, there's my g of x. And then I've got my f of x. It's going to go like this, right? More or less, okay? It's a pretty bad drawing, but you get the idea. Okay, so, all right, here's the space. So when I rotate that around the x-axis, I'm going to get this shape here. It was much better in my notes, but it's okay. Okay, so what you'll notice is that I have a hole in the middle. And that's the important part of this whole thing, right? I have this hole here, right? And it's going to be more visible. Okay. Let's draw another one down here, right? So there's my disc, but then I have this hole here, right? I'm trying to find the volume created by these two spaces down here, okay? This space and this space. I don't know, that's a very bad drawing. I wish I could draw it better. Okay, here I redrew it for us. Maybe this will make it a little bit easier to follow. Okay, so when we revolve that around, we get this shape, okay? And when we look at the shape, we have a large portion of this shape that is actually a hole, right? So this is a hole here, kind of like a donut or a washer, right? So if anywhere I draw these discs, it's not going to be a whole disc. There's going to be a big empty space in the middle there, okay? So what we're going to do is we have to take the volume of the larger one. So we're going to do pi big R squared minus pi little r squared dx, right? So we're going to take the integral. In this case, it's going to be from 0 to 2. Okay, so my volume equals the integral of pi big R squared minus pi little r squared. And this will be dx because it's perpendicular to the x-axis. Okay, now the big R, right? Big R is from the x-axis to the top function, which in this case is f of x. So big R is going to be 1/2 plus x squared, right? But it's r squared, so we're going to square that. And then, of course, little r, that's the going from here to the green line, which is g of x. So that's x, so little r squared is x squared. Okay, now let's translate that into our volume formula. So volume equals, okay, I'm going to take the pi out, right? 0 to 2, and it's going to be, I'm going to use a bracket here, 1/2 plus x squared minus little r squared, which is x squared, dx. Okay, and then we're going to go ahead and we're going to integrate that. So the volume will equal pi, that's the integral. Now I'm going to expand this. That's a 0. Okay, that's going to be 1/4 plus x squared plus x to the 4th minus x squared dx. So that's going to equal pi times the integral from 0 to 2. That'll be 1/4 plus x to the 4th dx. Okay, and I'm going to have to see if I can get some space here. It's better write a little bit smaller, huh? Okay, so the volume will equal, okay, we've got pi, and we're going to go ahead and integrate each of these. So this is going to be 1/4 x plus x to the 5th over 5, and we're going from 0 to 2. Okay? And don't lose track of that pi that's outside. I do that all the time, and it's so frustrating. Okay, so we'll substitute our 2 in there. So that's going to be 1/4 times 2 plus 2 to the 5th over 5 minus, and then we substitute the 0 in there, so we're going to get 0 minus 0, which is 0. Okay, so we get pi times 2 over 4, which is 1/2, plus 32 over 5, which comes out to 69 over 10 pi. Okay, that is the area found, or the volume of the solid that's generated, right? So we have this funky looking, think of it as a modern day vase, right? This is the solid that we're referring to, is this solid right here, right? And then this is the other side of the solid, and that's found by revolving it around the x-axis. But when we do that, we end up with a big old hole in the middle. Okay? Okay. That's a much better drawing up there, isn't it? All right, let's look at the next one. I'm going to just erase this space so I can have a little more room and write. And I'll try to do a neater job. Okay, so the next one, the volume of the solid formed by the region bounded by the graphs y equals the square root of x and y equals x squared. Okay, so y equals the square root of x, that is basically that right there, okay, square root of x, okay, and then y equals x squared, well, that's just going to be, that's going to be this curve here, right, x squared. Now we're revolving that about the y-axis, so that means, let's see, here's my x squared, right, and then this one's a little bit easier to draw, isn't it? And here's my square root of x, okay, square root of x and x squared. Okay, so I revolve it around there and I get this shape. Okay, and this is, sometimes if we just fill it in, it makes it a little bit easier to see. Okay, so that's the shape I'm going to get. And of course, if you look at this, we're going to have a hole in the middle also. These cylinders, or these discs, are going to go perpendicular to the y-axis. So here's my disc, right? And it's got this hole in the middle, so I'm making a washer or a donut. We think of it more as a donut than a washer, don't we? Okay, so here's my shape. Okay. Okay, so the first thing I have to do is find out the upper and lower bounds for my integration. So that means I need to find out where they're going to intersect, because we're going from here to here, whatever those points are. Okay, so square root of x is equal to x squared, right? So if I square both sides, I'm going to get x equals x to the 4th, right? So x to the 4th minus x equals 0. So I'm going to factor an x out, right? So they're going to intersect at x equals 0 and at x cubed equals 1, or x equals 1. That's where they're going to intersect. Is that correct? Did I do that correct? Yeah. Okay. Okay. So I drew that incorrectly. So that means they're intersecting right here and here, right? So the original curves, right? There's one curve and there's the other curve. The original curves are intersecting at 0 and 1. So I had to find those points of intersection. That tells me my upper and lower bounds, right? Okay, so let me just erase this so that we have some space. Okay, so I need to take the volume now, okay? Of course, the volume is going to be pi times the integral from 0 to 1, right? Big R squared minus little r squared. And this has to be, we're rotating it around the y-axis, so this has to be in terms of y instead of terms of x. So now that means we have to do a little bit more work because these equations are in terms of x. So let's just go over here and let's rewrite the equation, right? So we have y equals the square root of x, right? But I need to rewrite it so that it's in terms of y instead. So I'm going to square both sides. So that means that x is equal to y squared, okay? So the square root of x, the blue function, right, is x equals y squared, all right? So I'm actually going to rewrite these, right? This is y squared, okay? And then the red function, right? The red function is y equals x squared. So we'll take the square root of both sides, so we get the square root of y equals x. So this is the square root of y. So be really careful, label it so you don't lose track of what's actually happening, okay? Okay, so now let's look at our actual function, right? So my big R is going all the way out here to this red one, which is the square root of y. So big R, or I should say big R squared, is the square root of y squared, okay? And then little r, all right, that's right here, okay? Little r squared is y squared squared. Okay, so now let's go back over to our volume. So we're doing pi, the integral from 0 to 1, big R squared, so that's going to be the square root of y squared minus little r squared, which is y squared squared dy. Okay, so this is going to equal pi, integral from 0 to 1 of y, square root of y squared is y, minus y to the 4th dy, which is equal to, okay, we're going to go ahead and integrate that, so there'll be y squared over 2 minus y to the 5th over 5, and we're integrating from 0 to 1. So that's going to give us pi times, substitute 1 in there, so 1/2 minus 1/5, right? Minus, and we'll substitute a 0 in there, so it's just 0. So this equals 3 over 10 pi. And just make sure you understand what we did on this one. Okay. So because we are rotating around the y-axis, instead of having y equals something, I need x equals something. So this was kind of a confusing one because even when I solved for x instead of solving for y, they looked similar. So I had to be really careful about how I labeled these functions, okay? And remember, the volume, when we have a washer method, is going to be the integral of pi big R squared, that's the larger cylinder, minus pi little r squared, that's the smaller cylinder, right? This is the area function, right? Pi r squared dx or dy, depending on which it is, right? So what we're doing is we're factoring the the pi out of there. So we just have big R squared minus little r squared. Okay? Okay, let's continue looking at more examples. Okay, now we've got a solid generated by rotating the region about the x-axis. Okay, so that's good. All right, so when I rotate this around the x-axis, right, I'm going to get, let's see, curve that looks kind of like this. Let's see. Okay, so, all right, so I get that. Okay, there's my solid. Okay, so now when I slice my discs out of here or slice my washers, right, here's my open section in here. Okay, all right, so which one is, let's see, we've got y equals x minus 1 squared plus 2. Okay, y equals x minus 1 squared plus 2, right? That's the parabola. Okay, so that means, right, I'm going to do that in blue. That's this top one here. That's our parabola, okay? And then the other one, that's the y equals x. That's the linear one, okay? And that's right here. That's my green one, okay? Okay, it says write the area of a single slice. So the area is going to be pi big R squared minus pi little r squared. Okay, so my area. Okay, and this is, sometimes you'll see free response questions that are kind of worded like this, right? Equals pi, okay, the big R, right? Big R is going all the way up top to the parabola one, right? So that's going to be x minus 1 squared plus 2 squared, okay, minus pi r squared, the little one, right? So that goes up to here to the green line. So that is pi times x squared. Okay, so that's my area of a single slice. Now it says write an integral for finding the volume of the solid. Okay, so we're finding the volume of the solid, so that means we're looking for, right, volume equals the integral. Oops. Yeah, I'll do it that way, that's fine. And this is going to be pi big R squared minus pi little r squared dx, okay? So now we have to figure out, let's see, how far are we going? Let's see, generate by rotating it, y equals x and x equals 0. Okay. Oh, they have it marked here. Here we are, x equals 2 right here. They have it marked. Okay, so we're going from 0 to 2. Okay. So this is going to be pi times the integral from 0 to 2 of I'm going to use a bracket there, x minus 1 squared plus 2 squared minus x squared dx. Okay. And this is a calculator problem. So I put this in my calculator, and when I did that, I got the volume equals 26.389. Okay, so I'm going to just refresh your memory on how to do it on the calculator. So I put my big R, I put that in Y1, and I put little r in Y2. Okay, so now I'm going to go to math and go down to number 9, FNINT. We're integrating from 0 to 2. And we're doing big R squared, so that's Y1 squared, that's big R squared, minus little r squared, so that's Y2, and we do squared. Okay, and this is with respect to x. Okay, I get 8.4, but then I have to multiply that by pi, and we get 26.389. Okay, it did say to round to 3 decimal places. Okay. Okay, number 9. A solid plastic sphere of radius 5 inches will have a hole bored out of the center with a radius of 3 inches. What is the volume of the resulting plastic sphere? Okay, so they've got a little picture of the sphere down here. Okay, so the radius of this hole is 3, right? The radius of the sphere is 5, all right? So what am I actually looking at? Okay, so if I were to revolve that around the x-axis and to get an actual hole, right? A hole that has a radius of 3. So these are kind of weird, and after you see it, then you're kind of like, oh, I get it, but it's hard to visualize the first time. So what we're actually looking at, right, is if I had, what happened here? I just lost my marker. 4, 5, 4, 5, right? So I'm actually looking at something like this. Okay, so if I had this shape here and I rotated it around the x-axis, right, it would give me a sphere with these open ends here. Okay, I'd have like open ends like that. Okay, so it's this sphere I have to figure out. Well, what it actually is, it's a circle. It's a circle centered at the origin with a radius of 5. X squared plus y squared equals 5 squared. So if I were to solve for y squared equals 25 minus x squared. So y equals the square root of 25 minus x squared. Okay, so that would be the positive circle, but we're also bound by this line here of y equals 3, right? So what I'm doing is I'm taking this circle, but I'm only taking the region it's bound here, right? The full circle, or the full semicircle, because it's just the positive part of it, would be this whole thing. But because it says that I have this hole in the middle with a radius of 3, I know that I'm not taking all of this. This is all like bored out space there. So I'm only looking at this bound region right here. Okay, so my area, right, is going to be big R squared, right? Big R squared. And let me just do my cylinder here. Okay, and here's my hole in the middle. Okay, so our big R squared, that's going to be the square root of 25 minus x squared, right, times pi. Okay, minus little r squared, which is what? It's 3 squared times pi. Okay, so my area my formula is actually going to look like this. Area A of x equals pi times right? Square root of 25 minus x squared minus minus 9, or 3 squared, okay? Okay, so what's the interval that I'm talking about? Well, this is kind of a tricky problem, okay? What are these points here? Okay, where do they intersect? So where does the square root of 25 minus x squared intersect with 3? Well, that's 25 minus x squared. If I square both sides, equals 9. So we get negative x squared equals negative 16. So x squared equals 16, which means x equals plus or minus 4. So these are intersecting at plus or minus 4. Okay. So my integral is going to look like this. It's going to be the volume equals pi times the integral from negative 4 to 4, okay, of square root of 25 minus x squared squared, which means it's just 25 minus x squared minus 9 dx. Okay, we can simplify that a little more. Pi times the integral from negative 4 to 4 of 16 minus x squared dx. Okay, what is the result, the volume? Okay, so if I put that in my calculator, I can find my calculator. Okay, so I'm going to do math. Number 9, I'm going from negative 4 to 4. And we said that was 16 minus x squared dx. Oh, and we're going to multiply that times pi. See, I almost forgot that. Right? 268.083 equals 268.083, and that we have a unit here, so this will be cubic inches. Volume is going to be cubed. Okay? Okay, so I am going to pull up the homework exercises for this section. Okay, so we're going to look at number 6. We did numbers 1 to 5 already. Okay, so we've got, this is rotating around the y-axis. So we want to solve for x, which we already have. Okay, so in order to actually get a visual of this, I'm actually going to rewrite it in terms of y. So if I take the square root of both sides here, I get y equals the square root of x. So that helps me out here. This is y equals the square root of x, right? Or I'm going to say x equals y squared, right? And then the other one, okay, this one we're going to have y equals 1/2 x. Okay, again, this is just to help me get a visual graph of it. Okay, so that's going to be this right here. So this is x equals 2y, okay? This is going to rotate around the y-axis. Let's see here. Okay, so we're talking about this space in here. And that means our cylinders or our disc looks like this with a space here. Okay, it looks like it's a little bit hard to see with that black in there, isn't it? Okay, let's try that again. So here's one curve, there's the other curve. Okay. Okay. You can see it a little bit better like that. Okay. Okay, so next thing I need to do is find out where they're intersecting. And it looks pretty clear that it's one of the points of intersection is 0, 0. But in order to do that, we're going to set these equal. So I'm going to set square root of x equals 1/2 x. So I will square both sides. So we get x equals 1/4x squared, right? So let's multiply by 4. So we get 4x equals x squared. So 0 equals x squared minus 4x. Factoring out an x, we get x times x minus 4. So we're looking at x equals 0 to 4, right? But we're rotating around the y-axis. So when x is 0, y is 0, right? 0, 0. When x is 4, right? X is 4, so y is going to be the square root of 4, which will be 2. So we're going from 0 to 2. Okay, so our volume equal to pi times the integral from 0 to 2. And we're looking at big R squared, okay? So big R, that's going all the way out here. And that line is this line right here, which is the 2y. So that's going to be 2y squared. And then little r squared, right? That's going to be just here. And this curve is y squared. So it's going to be y squared squared, okay? So remember, our volume is pi times the integral from a to b of big R x squared minus little r of x squared dx, right? So big R squared is, in this case, we're talking about y, not x, sorry. Oops. About y, this case, in this time instead of x. Okay, so big R is 2y squared minus little r, which is y squared squared dy. So our volume is pi times the integral from 0 to 2 of 4y squared minus y to the 4th dy. This is a non-calculator section, so we have to do this by hand. So this will be pi times the, oops, not times the integral, pi times, this will be 4y to the 3rd over 3 minus y to the 5th over 5. And we're going from 0 to 2, which comes out to pi times, that's 32 over 3 minus 32 over 5. And then, of course, it's minus 0. So that equals, so the way I did this to make it a little easier, because these are big numbers, right? I factored out a 32. So 32 pi. That left me 1/3 minus 1/5. That's a whole lot easier to work with when you don't have a calculator. So that's going to be 32 pi. And this is going to be 5 over 15 minus 3 over 15. So we get 32 pi times 2 over 15. Oops, forgot my pi. Which equals 64 pi over 15. Okay. Okay, let's look at number 7. Okay, and again, you don't have to sketch it, but I think it's very difficult if you don't. Okay, we've got the line y equals x squared. Okay. And we've got, okay, so y equals x squared. That's actually, it's the full parabola, right? We've got the line y equals x plus 2. So let's see, 1, 2. Right, let's see, 1, it's got a slope of 2, up 2 over 1, up 2 over 1, right? Okay, so there's that line there, right, and that's going to keep on going down like that, okay? And x equals 0. Well, x equals 0 is the y-axis. So that's how, once I saw that, I'm like, okay, so that means that I'm not dealing with anything over here. Okay. Okay, that is revolving about the x-axis. Okay, so it's going around the x-axis. And y. Okay. Okay, so there's our shape. Okay, and okay, there's the top of my shape, right? Okay, so when I take my slice, here is my disc, right? Here's my hole, right? So there's the washer that we're looking at. Okay, okay, so my integration, right, my volume is pi. I'm integrating, right, big R of x squared minus little r of x squared dx. So I need to know my limits of integration. So when they don't tell us, we have to figure it out. So basically, when I rotate this, the solid that's formed, right, the solid that's formed is the solid that's bound between these two curves. That means I have to find where those two curves intersect. Okay, just like we did in the previous one. We got to figure out where they intersect. So that means I need to know where x squared is equal to x plus 2. So x squared minus x plus 2 is equal to 0. Oops, x minus 2, sorry. X minus 2 equals 0. This one we would factor x minus 2, x plus 1 equals 0. So we're looking at x equals negative 1 or positive 2. Well, since we're only here in the first quadrant, this x equals negative 1 is not going to be considered. So I'm actually looking at x equals 2. So these two curves are intersecting at 0 and at 2. Okay. Did I do that correctly? I guess I did, yeah. Okay. So that means we're integrating from 0 to 2. Okay. Okay, now the big R. Big R of x, right? The big one is going all the way up to the linear function. So that's going to be the x plus 2, right? The little r of x, that's the parabola. So that's the x squared, okay? So we've got a volume going from 0 to 2. And we have x plus 2, that's the big R squared, minus the little r of x squared squared. Okay? So we will expand this out. Okay, so this is going to be, I forgot my pi here. So important. Pi times the integral from 0 to 2. And this is going to be x squared plus 4x plus 4 minus x to the fourth dx. Okay, so when I integrate that, we get pi times x to the third over 3 plus, this is going to be 4x squared over 2, 4x squared over 2, right? But that's going to reduce to 2x squared, right? 2x squared plus 4x minus x to the fifth over 5, right? And we're evaluating that from 0 to 2. So that's going to give me pi times, substituting 2 in there, 8/3 minus 8 plus 8 minus 32 over 5. And again, this is a non-calculator section, so I'm going to do that same trick again. I'm going to factor an 8 out of there, and that's going to give me 1/3 minus 1 plus 1 minus 32 over 5, okay, which is 8 pi times 1/3 minus 32 over 5. I'm sorry, it's not 32. I took an 8 out, didn't I? That's going to be 4 over 5. Something's wrong. Oh, this is a plus. There you go. Plus 2 minus 4 over 5. Okay, so common denominator, so that's 8 pi times 5 over 15 plus 30 over 15 minus 12 over 15, which equals, let's say, 35 minus 12 is 23 over 15, right? 8 pi times 23 over 15, which equals 184 over 15 pi. Okay? Okay, number 8. We're revolving around the y-axis. I'm going to graph them in terms of x first, and then I'll rewrite the equations again. So y equals 2x, right? Crosses 0, 0. Okay, has a slope of 2, so up 2 over 1, up 2 over 1. Okay, so, all right, there's my linear function, all right? And then the other function is parabolic. So we're looking at 0, 0, 1, 4. Okay, okay, so that's going to be a little bit hard to see. All right, so I think what I'm going to do, before I continue graphing it, I'm going to check to see where these actually intersect. So we have 2x equals 4x squared. Okay, so that means 4x squared minus 2x equals 0. So we'll take a 2x out of there, so that's going to be 2x minus 1. So they're going to intersect at 0 and at 1/2. All right, so I'm going to regraph this because it's too hard to see the area that they intersect. Okay, so we'll make this 1 out here, which means this is 1/2. Okay. Actually, let's just go ahead and make it 1/2. I don't know why I did that. Okay. So when x is 1/2, y is 1. Okay. So x is 1/2, y is 1. That's my linear function. Okay. And then when x is 1/2 right? I have 1/4, 1/2 squared is 1/4 times 4 is 1. So this is going to be a parabola, right? And it's going to be going like that, okay? Intersecting there at x equals 1/2 and y equals 1. Okay? Okay, so let me just erase this to make some space. Okay. Okay, so let's see. We need to rewrite these because we're rotating around the y-axis. Right, so looking at, oh bad, that's really bad. Okay, there's the linear, and then here's the parabolic curve. Something like that, okay? And that means we've got, okay, when I take my slice out, okay, here's my hole. Okay, so since I'm rotating around the y-axis, I have to rewrite these solving for x. So here, x is going to equal 1/2 y. And let's see, if I take the square root of both sides, I get the square root of y equals 2x. So we're looking at x equal to 1/2 square root of y, okay? So labeling the functions here, this blue one, this is 1/2 square root of y. And then, of course, the red one is the 1/2 y, okay? Okay, so our volume is pi times the integral, okay? Where is it intersecting in terms of y? It's intersecting at y equals 1. So we're going from 0 to 1, okay? Rx, big Rx, or Ry rather, Ry, okay? So we're going from here all the way out, Ry. That's going to be the parabolic function, which is this one right here. So we're looking at 1/2 square root of y. All right, so this is going to be Ry squared, so it's 1/2 square root of y squared minus, okay, little ry, right? So little ry, that's the linear function, which is the 1/2 y. So it's minus 1/2 y squared dy, right? Remember, it's ry squared minus little ry squared. Okay, that's our formula. Okay, so let's work through this one. So we have the volume equals pi times the integral from 0 to 1. Okay, when I square this, I get 1/4 y minus, squaring that, 1/4 y squared dy. Okay, so we can pull the 1/4 out of there. So we get 1/4 pi integral from 0 to 1 of y minus y squared dy. Okay, so the volume equals 1/4 pi. Okay, we're going to integrate this. So this is going to be y squared over 2 minus y to the third over 3, going from 0 to 1. Just got to bring it back up here, okay? Equals 1/4 pi. Okay, we're going to substitute the 1 back in there, so that's 1/2 minus 1/3. And then when we substitute the 0 in there, it just ends up being 0, right? Okay, so we have 1/4 pi. This will be 3/6 minus 2/6 which equals 1/4 pi times 1/6, which gives me 1/24 pi. Okay. All right. I think that we will stop there. This because the rest is just more of the same. If you look at this, I'll just kind of step you through this. But this has got, let's see, y equals 6 minus x squared, x equals -2, and x equals 2. Okay. And then 6 minus x squared, that's going to be an upside down parabola crossing the y-axis at 6. So we've got, it's going to do something like this, right? Okay. Where do these intersect? Let's see here. Okay, so this is revolving around the x-axis, so obviously we actually don't need to know where they intersect. If this revolves around the x-axis, I'm going to get a curve that looks like this. So there's no hole there. This is not, right? This is not a washer, right? It's going to revolve around the x-axis, right? So basically I'm getting a big gigantic, it's kind of like a ball with blunt ends. Okay. So it's kind of like, see if I can clean this up a little bit. Okay, so I'm getting sort of a shape like this. It's just this shape here. And then when it's going around the x-axis, so when I make my slice, there's no hole in there, right? This is just a disc coming out of here. Okay, so this volume is pi, and the integral, it's revolving around the x-axis, so it's going from here to here, which is -2 to 2. And the radius, right, pi r squared, right, dx. So the radius in this case is going to be the parabolic function. So it's 6 minus x squared dx. This is a calculator piece, so I just put that in my calculator and we get, oops. Sorry, hold on a second. We get 291.540. So sometimes it gets a little confusing because we're so used to doing the washers, but they're not always washers. They might just be the disk method, okay? The next one, this one is very similar to number 8, actually, okay? So when we graph it, we'll see that we have a linear and then a parabolic function. It's revolving around the y-axis. So it's actually very, very similar. The only difference is this function y equals 1/8 x cubed. That's actually going like this. But because it's bound between x equals 0 and y equals 0, we're only talking about this quadrant here. Right? So I'm not concerning myself with that part there. Right? And then we have a linear function. So we end up with the same type of shape, okay, revolving it around the y-axis. So we have the same type of thing going on that we did in the previous problem, okay. So that my disk And my washer looks like this. Right, here's my hole. Okay, so this one, the only tricky part here is that we have to put it in terms of x. So x will equal 1/2 y. Okay, that's a linear function. But then the next one, right? So I'm going to multiply by 8 on both sides. So we have 8y equals x to the third. And then take the cube root of both sides. So we get 2 times the cube root, or I'll say y to the 1/3 equals x. Those are my two functions. We make sure that I did that correctly. Yes, okay. So then we have to find the limits, right? The bounds rather. So we know we're going from 0, but where are they intersecting up here? So we have to find where 1/2 y is equal to 2y to the 1/3. Okay. So let's see, doing that. Is that going to be easier? Let me see which one's going to be easier to do. Okay, so I'm just going to raise it both sides to the third power. So that'll be 1/2 to the third power, so that's 1/8. Y to the third equals 8y. Okay, so let's multiply by 8 on both sides. So we get y to the third equals 64y. So then y to the third minus 64y equals 0. So if I factor a y out, I get y squared minus 64, 0. So we know y equals 0. And we know y squared equals 64. So y equals plus or minus 8. Of course, we're only talking about the positive 8. So it looks like they're going to intersect at y equals 0 and y equals 8. So the volume equals pi times the integral from 0 to 8. Okay, big R squared. So that's the parabolic function, or not the parabolic, but the cubic function. So the cubic function is 2y to the 1/3 squared minus the little r squared is the linear function, so that's 1/2 y squared dy. Okay, and when I go through the process of working all of that out, this ends up equaling 512 over 15 pi. Okay. The next one, again, this ends up being, the trickiest part about this is sketching the graph, okay? First quadrant is bounded by this curve, okay? So this is, you know, how do we know how to graph that? Well, I started off by just kind of looking at some points, right? When x equals 0, y equals 27, okay? So then what else can I do? Let's see, where's it going to cross the x-axis, right? That's when y equals 0. Oh, this is a calculator problem. Ah, that's silly. Okay, so doing it on your calculator, you're going to find it's going to cross the x-axis at 9, all right? It's bound by that curve, the x-axis, and the y-axis. So that's the region I'm talking about. It's revolved around the x-axis. So we can see that this is not a washer method. This is just a disk method. Okay, so this is just a disk method. So our volume is pi integral from, it's the x-axis, so from 0 to 9 of r squared dx, okay? So, and r is, of course, this function here. So this comes out to be pi times the integral from 0 to 9 of 27 minus x to the 3/2 squared dx. We're using our calculator, so this comes out to 9,275.395. Okay, Last one. Let's see, this is parabolic. Okay, the line x equals 4. And the x-axis. So we're revolving this region here around the x-axis. Okay, so that's going to be over here at -4, right? So there's my region. Right, so this is going to be a washer. Right, that's going to be a washer. So once again, we have to solve for x. So y equals x squared, so x equals the square root of y. Okay. Where are they going to intersect? Right, so we've got, let's see, y equals x squared, so x squared is equal to 4 at x equals plus or minus 2, okay? If x equals 2, then y equals 4, okay? Make sure that I've read that correctly. Yes. Okay. So this is going to be your volume equals pi. We're going to integrate from 0 to 4. Okay. And big R in this case is the line 4, right? X equals 4. So that's 4 squared, big R squared, minus little r squared, which is the square root of y squared dy. And then you can integrate that on your calculator. Okay? Okay, so that is volume using the washer method. And again, it's this, you just have to memorize, or you just have to remember that you're using, whoops, I'm on the wrong thing here, sorry. You're using the formula big Rx squared minus little rx squared, okay? One of the common mistakes that is made with this is that students will do this. Big Rx minus little rx squared, right? So that's incorrect. You square each of them separately. It's big R squared minus little r squared. So we're taking the volume of the big one and we're subtracting the volume of the little one, okay? And then, of course, if it's revolving around the y-axis, everything has to be in terms of y, which means you solve for x. Okay.